Welcome back everyone. In our last video we discussed on the factor affecting resistance, and in this factor we said that the resistance depends on the resistivity of the material, the length of the material, the cross-section area, and the cross-section area and the nature of the material applied. Now we are going to be looking at the effect of temperature on a substance. So in this effect of temperature, since we know that we have different types of conductor, so we have metallic conductor, we have non-metallic conductor, we have insulator, electrolyte, we have gas. And in all this material, we have each one have its own uses. In metallic, we already know from word metal, something that conducts what? Electricity. So, like something that conducts electricity, insulator, a material that does not allow the passage of electricity to pass through it. Also, we are familiar with semiconductor. So this semiconductor, they are intermediary between a metallic conductor and also an insulator, because in some cases this metallic conductor, they act as what? They act as a metal. Sometimes they act as what? Insulator. So we also have electrolyte, we also have gases. So in this one, all these gases, electrolyte, they are also factors that we normally consider when dealing with electricity, because in some time we can use gases to conduct electricity. It's just that the electricity that we generate from gases will be very small. Now, if we look at for the metallic conductor, we said that the resistance is directly proportional to the temperature. It means that if we increase the resistance of a metallic conductor, then the temperature of the temperature also will what? The temperature also will increase. And if we reduce the temperature, so the resistance also will reduce. This example, if we deal one, I don't know whether you do a practical that deal with determining of what? Measuring of resistance by some quantity, in which you are going to test the temperature, you are going to measure the resistance when the temperature is at ice, and you are going to test the temperature, the resistance of the substance in which when the temperature is at steam. We see that when we have a steam temperature, so the resistance will be at high value at that time. So, and when we are in ice, we see that the resistance will also fall because of the proportionality limit between the two substances. And this insulator also, in the case of insulator, the resistance of insulator is inversely proportional to the temperature. So it means that the resistance decreases as the temperature increases, like that one. Then we have for semiconductor. For semiconductor, when the resistance of a semiconductor reduces, when the resistance decreases, then the temperature of the semiconductor will reduce. So it is also inversely proportional there. In case of electrolyte, the same thing. In electrolyte, resistance of electrolyte decreases and also the temperature increases. It means that in electrolyte also, the resistance of electrolyte is also inversely proportional to the temperature applied to it. So, and for gases, we say at high temperature and low pressure, so the resistance of a gas matter decreases. So these are the conditions for the what? These are the effect of temperature on all these substances. And the effect of temperature on the metallic conductor itself. So if you have a metallic conductor that have a graph, this is R naught, and this is theta. Actually, this theta means change of temperature, because we are changing it from, let's say, theta 2 to theta 1. Let me just say change in temperature. So the equation of this graph is clearly equal to R equal to R naught alpha delta theta plus R naught. If you compare this equation 1 with equation of straight line, we are going to have the equation of straight line is actually y is equal to mx plus c. and our y is the same thing as the resistance. So if you look at it, x is here and c is r0. That's the intercept, and this x is alpha change in temperature. Because we are plotting the graph of r against what? The graph of r against alpha against r, the graph of r against r0. If we are plotting the graph of r against r0, then the slope will be equal to what? The slope will be equal to alpha change in temperature. So we are plotting, this is our x, because this is x-axis. So this against this, and our slope will be equal to alpha r0. Our intercept will be equal to r0. So from this equation, I can say that r is equal to r0 into, then this one will remain 1 plus alpha change in temperature. Let's say this is equation 2. This is the formula to find the what? The resistance of a metallic conductor, in which R is the what? R is the resistance at temperature theta. R naught is the temperature resistance at 0 degrees Celsius. That is the ice temperature. So if we are to raise the ice temperature to a certain temperature, call it theta, so we call it R. And our alpha is the same thing as what? Theta, the theta, which is theta 2 minus theta 1, is the same thing as change in what? Change in temperature. So it's change in temperature, and our alpha is the temperature coefficient. This one is coefficient of temperature. So the coefficient of temperature. This is the coefficient of temperature. If for two resistance R1 and R2 at theta 1 and theta 2, then we are going to have what? At theta 1 and theta 2, we are going to have two equations. The equation of R1 and the equation of R2. So from our formula, we say that R is equal to this. Clearly, our R1 will be equal to R0 into 1 plus alpha change in temperature 1. Let's say this one is equation 3. And R2 will also be equal to R0 1 plus alpha change in theta 2. Let's say this is equation 4. If we are to solve this, we just say this one divided by this, equation 3 divided by equation 4. If you solve the mathematics, if alpha change in temperature is small, then we are going to have what? If you combine these two equations together, so we are going to have R2 to be equal to R1 into 1 plus alpha change in temperature. Let's say this is equation 5. So this is the formula to relate two resistors together at a certain temperature. if alpha delta theta 2 is small. If this one is a very small element, that is infinitesimal element. So you know, in some cases, if you have something like sin theta to be equal to cos theta to be equal to tan theta, you can say that everything here is equal to theta. If we are dealing with a very small element, that is, if sin theta is small, the cos theta is small, the tan theta is small, then all of them will be equal to theta. We call them angle at infinitesimal. Angle at infinitesimal. So now it means that if you are given two resistance, we are going to apply this. But if you are given a resistance at ice and at a certain temperature, then we are going to consider our equation 2, which is derived from this equation here. So then also we have change of resistivity with temperature. The change of resistivity with temperature. You know that if we consider from our formula, we say that resistance is equal to rho L over area. And you know, if you want to change resistivity with respect to temperature, from our formula, our resistivity here, resistivity is equal to RA over what? Over L. But to change this in terms of resistivity, conductivity, the conductivity is equal to what? You know, it is the same thing as 1 over resistivity. So if we solve the mathematics, our formula, let me just write the formula directly. Our formula, in terms of R1 and R2, in terms of two resistance, we are going to have ρ2 to be equal to our resistivity. If we make it a subject of formula here, we are going to have RA over L. So if it is in terms of this thing, we say R1, then resistivity will also be equal to R2, A1, AL1, L2, A2, L2. Sorry, L. Okay, yes. If we solve this thing with respect to this, we are going to have something like this: ρ1 into 1 plus alpha change in temperature. Let's call this equation 6. Let's look at one example here. Okay, because of time, in our next video we are going to be solving example in which we are going to relate the resistance, the question that contain resistance and resistivity together. Now my advice for you is that you should try and look for more questions on all these aspects and try and solve them. Sometimes when you are solving question, you actually see that you cannot solve that question. Try and solve the question again. If you also cannot solve it, try and solve it again. By the time you try, you will actually get the way to solve that question. In fact, in some cases, even when I too am solving question, in some cases it used to take me a week, sometimes some question for a month, and I will continue to be trying it. So sometimes I will just see the solution to that question. So, but if you are not the one that is trying, so it will not be easy to actually be able to solve problem in physics. Solving problem in physics deal with more parties, so you have to practice well. So please endeavor to like and subscribe to this channel to see more of this video. In our next tutorial, we are going to be dealing with the solution, the example on all the factors that affect the metallic conductor with respect to what? The temperature. And also we are going to solve the example that relates the arrangement of parallel and a series connection together, in which we are going to see how a current is passing through them, how we can calculate the current for each connect for the parallel in the combination and for the series in the combination. And we are going to look at to calculate the voltage across each resistor. Thank you for watching this video. See you next time.